Section 11.6 is about absolute convergence and the ratio and root tests. Let's call this 11.6a. So if we have any series, the series of a sub n, then we can consider the corresponding absolute value series, which is the absolute value of a1 plus the absolute value of a2, and so forth. So you can see that what we would be doing is looking at the absolute value of each term. So we have a definition, and it says a series AN is absolutely convergent if the series of the absolute value of terms is convergent. So here we have absolutely convergent, and we're going to learn that if it's not absolutely convergent, it could be conditionally convergent. So let's look at an example. The example says the sum from n equals 1 to infinity. And we have the alternating series, negative 1 to the n minus 1 power over n squared. Now these terms are 1, and if you put in 2, you have a negative 1 over 4. If we put in 3, we have a positive 1 over 9. If we put in 4, we have negative 1 over 16, and so forth. So let's look at, let's say consider the sum of the absolute value of negative 1 to the n minus 1 over n squared. Now that means we take out the alternating series part, so we have the sum of 1 over n squared, and that's always positive. So we can think about that term. And this is a p-series. This is a p-series with p equals 2, which is greater than 1, so this is a convergent p-series. So since the absolute value is convergent, we can say, therefore, the series of negative 1 to the n minus 1 over n squared, that this is absolutely convergent. So absolutely convergent. Let's look at another one. The example says the sum from n equals 1 to infinity. We're going to do the alternating series, so it's negative 1 to the n minus 1 over n. So let's consider, let's look at the terms. We have 1 minus 1/2 plus 1 over 3 minus 1 over 4, and so forth. So let's consider the absolute value of such. The sum of the absolute value of negative 1 to the n minus 1 over n. So that takes out the alternating series part. So we have the sum from n equals 1 to infinity, and we have 1 over n. Now we know two things about this. There's two ways you could go with this. First of all, this is the harmonic series, because it's 1, 1/2, 1/3, 1/4, and we know this is divergent. Or this is a p-series with p equals 1, and it's divergent. You have to know one of the two. You can go either way on it, but you have to know one of the two. So it is divergent. But if we look at the alternating series, so the sum from n equals 1 to infinity of minus 1 to the n minus 1 over n. So by the alternating series test, we know that the b sub n plus 1 is less than or equal to b sub n because the terms are all decreasing. So then we consider the limit as n approaches infinity of 1 over n. So this is 1 over infinity, which equals 0. which is less than 1. It's a value less than 1. Therefore, we can say that the series from 1 to infinity of negative 1 to the n minus 1 over n is convergent. So you can have convergence without absolute convergence. And this is the classic example. Your harmonic series, the absolute value is divergent, but the alternating series is convergent. So if we go back to the definition, it says that the series is absolutely convergent if the absolute value series is convergent. So we have a couple cases here. Whenever we look at a series, we have two options. It can be divergent or it can be convergent. Now, a convergent series has two options. It can be absolutely convergent, or it can be conditionally convergent. So the conditionally convergent. So the harmonic series is conditionally convergent. So we could come back here and say, therefore, the series, the alternating series, is conditionally convergent. So the problems in this exercise start off with, is it conditionally convergent or absolute convergent? If it's absolutely convergent, either way, you start off with looking at this absolute value. And if you have convergent, then you have absolutely convergent. So then you just need to check if you have convergent or absolutely convergent. This is a good chart to follow. It's a great diagram to help you think about it. You have a theorem in your book that says if the series is absolutely convergent, then it is convergent. So if you have absolute convergence here, then you have convergent for the entire series. So let's look at another example. It says, consider the series, the sum from n equals 1 to infinity, cosine of n over n squared. So this is cosine of 1 over 1 plus cosine of 2 over 4 plus cosine of 3 over 9. Now, whenever we look at trigonometric functions are always in radians. So the problem with this is it's not alternating. Some of the signs are positive, some of the signs are negative because we're in cosine and we're in radians. And pi over 2 is about 1.57. So cosine becomes negative on the second term, and it's still negative on the third term, and it's still negative for cosine of 4. It becomes positive again after 3 pi over 2. So this is not an alternating series, but the signs are positive and negative. So this absolute convergence is going to help us because we're going to consider, let's take that back and let's put consider. Consider, suppose, let, one of those words, the sum of the absolute value of cosine of n over n squared. Now, let me remind you, you're going to need words in here. You can't just throw this on here. You have to say this is what we're looking at in some way. So when we do this, n squared is positive, so let's call it the sum from n equals 1 to infinity of cosine of the absolute value of cosine of n over n squared. The best way to look at this is, do you see that the bottom is a p series where p equals 2? So let's do the comparison test. So then, or compare to cosine of the absolute value of n over n squared is less than or equal to 1 over n squared. Since this is true, then we need to look at 1 over n squared. So we say also the sum from n equals 1 to infinity of 1 over n squared is the p series where p equals 2, which is greater than 1, which says it's convergent. Therefore, the sum of the absolute value of cosine of n over n squared is convergent, which tells us that our main series, thus the sum from n equals 1 to infinity of cosine of n over n squared is absolutely convergent. Since it's absolutely convergent, then whether it's positive or negative, it's convergent. So that's very helpful. So let's look at number 6. And it says the sum from n equals 1 to infinity, negative 1 to the n minus 1 times n over n squared plus 4. I like my negative 1 on top, but they put it beside it. It's good either way. So the directions say determine if the series is absolutely convergent or conditionally convergent. So let's look at the absolute value. Look at it as a better phraseology there. The absolute value of the alternating series of n over n squared plus 4. So that takes away the negative 1 power. Do we need absolute value on the top? Absolute value of n. We don't need it on the bottom. N squared plus 4 is always positive. But n starts with 1 and goes to infinity, so it's always positive as well. Oh, now see, I see a p-series happening here, maybe geometric. So let's say consider. Whenever we're going to do a comparison test, we're going to look at the leading term. The leading term in the top is n. The leading term in the bottom is n squared. And this reduces to the sum of 1 over n. Now think about this series of 1 over n. We have two options here. It's a p-series with n equals 1, or it's a harmonic series, but either way it's divergent. That means we don't have absolute convergence. So now we need to consider the alternating series. So let's look back at the series from n equals 1 to infinity of negative 1, n minus 1, n over n squared plus 4. And the alternating series, first of all, it should be decreasing. Let's look at a few terms. If we put in 1 for n, we have negative 1 to the 0 power, so it's positive. 1 over 5. If we put in 2, we have a negative 2 over 8, which is 1/4. 3 would be positive, 3 over 13. 4 would be negative, 4 over 20, which is 1/5. 5 would be 5 over 29. And it may not be decreasing everywhere, but remember it must be eventually decreasing. So 1/5, 1/4, that's a little more than 1/4. We're back to 1/5, and then it goes down because that's close to 1/6. 5 over 29. So that's true. Now we can look at the limit as n approaches infinity of the term n over n squared plus 4. You have two options. We can look at L'Hopital's rule. If you're going to use L'Hopital's rule, you need to notate it as such. We're going to use L'Hopital's rule here. The limit as n approaches infinity. Remember, L'Hopital's rule is the derivative of the top, which is 1. The derivative of the bottom, which is 2n. So now we have 1 over infinity, which is 0. And 0 is a number less than 1. Therefore, the alternating series is convergent. But it's not absolutely convergent. It's conditionally convergent. So we say the series is conditionally convergent. So now we can look at the ratio test. There are two more tests in this section. The first one is the ratio test. The ratio test says First of all, I'm going to summarize it a little differently than your book would. It says if the limit as n approaches infinity of a of n plus 1 over a n equals L. So there are three cases here. Then case number 1, if L is less than 1, then the series of an is absolutely convergent and thereby convergent. So if your limit is less than 1, we have absolutely convergent. For 2i, if the limit is greater than 1, then the series is divergent. And 3i, if the limit equals 1, then the ratio test is inconclusive. Waste of time. It doesn't tell us whether it's convergent or divergent. That means try something else. So this is an important test that we're going to use. Let's look at an example. It says the series n equals 1 to infinity, negative 1 to the n. We have n cubed over 3 to the n. So we're testing this for absolute convergence. So we're going to use the ratio test. So using the ratio test, first of all, a sub n plus 1 means that I have negative 1 to the n plus 1, and then we have n plus 1 to the third over 3 to the n plus 1. So that means you put an n plus 1 everywhere there's an n. So we're going to use the ratio test, and we're going to say, we're going to look at the limit as n approaches infinity. Now this is a big fraction here, because we have a n plus 1 over a n. Sorry, I shouldn't have circled it that way. We need to look at this limit. So let's go back. A n plus 1 means we have negative 1 to the n plus 1, n plus 1 to the third over 3 to the n plus 1. And in the denominator, we have negative 1 to the n to the third, 3 to the n. Now, that's an interesting problem. Look at this crazy complex fraction. But remember, complex fraction means keep, change, flip. You're dividing by a fraction. So I'm going to keep the absolute value bars for a minute. We have negative 1 to the n plus 1, n plus 1 to the third, 3 to the n plus 1, divided by, so we can say times, negative 1 to the n to the third is on the bottom, and 3 to the n is on top. Now remember this 3 to the n plus 1. This really means 3 to the n times 3. Are you with me there? So let's be very specific about that in a minute. So we have the limit as n approaches infinity. Now the absolute value bars mean that these don't really matter because everything will be positive. So we have the absolute value of, here I have n plus 1 to the third, and like we said, 3 to the n times 3 to the n over n to the third. So these cancel, and we have the limit as n approaches infinity. We have n plus 1 to the third. Let's go ahead and use Pascal's triangle. So we have n to the third plus 3n squared plus 3n plus 1. Remember Pascal's triangle? These are your coefficients. So you start off with a 1, and you have n to the third and no 1. And here you have n squared, and you have 1. And you have n and 1 squared, and you have no n and 1 to the third. So all of this is being multiplied with the pluses in between. I like Pascal's triangle. I use it regularly in this area. So on the denominator, we have 3n to the third. Now, you can use L'Hopital's rule, but let's divide through by the highest power of n in the denominator. And you say, how do you know when to do which? Well, L'Hopital's rule, if you can use L'Hopital's rule, you can divide by the highest power of n in the denominator. If we use L'Hopital's rule, we would use L'Hopital's rule 3 times because we have an n to the third. So that's the difference here. If I divide by the highest power of n in the denominator, so if I divide by n to the third, I get 1 plus 3 over n plus 3 over n squared plus 1 over n to the third. And in the denominator, I just have 3. So when you plug in infinity, this goes to 0, this goes to 0, this goes to 0, and I have 1/3. So I have absolute, so we have absolute convergence. Because, sorry, I stopped right there. Because I have a limit less than 1, we have absolute convergence. Now, I'd like to do this problem for you another way. So I'm going to leave it for a second, pause, write down what you need. I'm going to go back and use L'Hopital's rule. So I'm going to pause and erase the ending. Sorry, is absolutely convergent. Okay, let's go back to here. So we have the limit as n approaches infinity. And in the numerator, we have n plus 1 to the third over 3n to the third. Now we're going to look at this using L'Hopital's rule. So if we were to plug in infinity, we'd have infinity over infinity. So using L'Hopital's rule, we take the derivative of the top and the bottom separately. And the derivative of n plus 1 to the third is 3 times n plus 1 to the second. And then times an understood 1 for the derivative of the inside, chain rule. And now the derivative of the bottom is 3 times 3 is 9n squared. Are you a cancel person? So this becomes 1 and 3. So now if we plug in infinity, we still have infinity over infinity. So let's use L'Hopital's rule yet again. And we have the limit as n approaches infinity. And the derivative of n plus 1 squared is 2 times n plus 1 to the first. And the derivative of 3n squared is 6n. I'm a cancel person. Let's cancel again. So now we can do L'Hopital's rule yet again and say the limit as n approaches infinity. The derivative of n plus 1 is 1. The derivative of 3n is 3, so we have 1/3. So again, we have absolute convergence because we have a number less than 1. So what I want you to realize here is when you get to something that looks like this, you can use L'Hopital's rule, or you can expand and do a basic divide by the highest power of the denominator, or use L'Hopital's rule. So you have several options at that point. It doesn't matter which way you go. You could go back to the original way we did it and expand it and use L'Hopital's rule a few times there. It's a little easier than the chain rule. So it depends upon which method you prefer. So now we're going to look at the root test, but I wanted to compare it to the ratio test. So the root test looks very similar to the ratio test, but it says if the limit as n approaches infinity of the root of the absolute value of an. Now this is the nth root. There can't be a number there. It is always the nth root equals L. Then, we should have it then over here. Case number 1, if L is less than 1, then the series AN is absolutely convergent. Case 2, if L is greater than 1, then the series AN is divergent. Case 3, if L equals 1, then the test is inconclusive and you need to do something else. So you can see how they're parallel here. So let's look at one of these. It says test the series n equals 1 to infinity of 2n plus 3 over 3n plus 2 to the n. Test it for convergence. So let's use the root test. So we say using the root test, the limit as n approaches infinity of the nth root of 2n plus 3 over 3n plus 2 to the nth is the limit as n approaches infinity of 2n plus 3 over 3n plus 2. Now here we have infinity over infinity. So you get to choose your method. Would you like to use L'Hopital's rule or divide by the highest power of n? I like L'Hopital's rule. So let's take the derivative of the top to be 2 and the derivative of the bottom to be 3. So the limit is 2/3, which is less than 1, so we have convergent. Therefore, the series n equals 1 to infinity of 2n plus 3 over 3n plus 2 to the nth power is absolutely convergent. I think we have time for one more, and then there won't be a second video. Number 26 in your book says the series from n equals 1 to infinity of negative 2 to the n over n to the n. So if you look at this problem, we can use the root test. So let's say using the root test, let's look at the limit as n approaches infinity of the nth root of negative 2 to the n, there's absolute value bars, over n to the n. Now that gives me the limit as n approaches infinity. The absolute value deals with the negative, and we end up with 2 over n, because the nth root takes away the n power. And that means we have 2 over infinity, which approaches 0, which is less than 1. Therefore, the series from n equals 1 to infinity of negative 2 to the n over n to the n is absolutely convergent. So I think you've got everything you need to do 11.6. Work through it carefully, and thank you.